Picture this: a silent, slow-motion collision of unimaginable scale. Two galaxies, each a swirling metropolis of stars, gas, and dust, drifting toward one another across the void. But this isn't a catastrophic crash, it's a graceful, almost choreographed encounter where gravity pulls them into an intricate dance that can last billions of years. What seems like destruction is actually creation in disguise. These galactic collisions are some of the most beautiful and transformative events in the universe, reshaping entire neighborhoods of stars and giving birth to new cosmic structures. And here's the wildest part: it's happening all around us, even right now, in the depths of space. You might think of galaxies as these serene, unchanging islands in the cosmos, but the truth is far more dynamic. They're alive with motion, constantly interacting, merging, and evolving. Our own Milky Way is no exception. In about 4 billion years, it's set to collide with the Andromeda Galaxy, an event that will rewrite the night sky forever. But instead of chaos, these collisions follow a kind of cosmic logic, a ballet of gravity, dark matter, and stellar winds that scientists are only just beginning to understand. And the most fascinating part, even in these titanic clashes, stars rarely actually smash into each other. The distances between them are so vast that galaxies pass through one another like ghosts, their structures bending and twisting into breathtaking new forms. So how does this celestial dance work? What forces shape these mergers, and what do they tell us about the universe's past and future? In this journey, we'll dive into the science behind galactic collisions, from the mind-bending role of dark matter to the stunning visuals captured by telescopes like Hubble and Webb. We'll explore how these events trigger bursts of star formation, how supermassive black holes at the hearts of galaxies interact, and why these collisions are essential to the story of the cosmos. By the end, you'll never look at the night sky the same way again, because out there, beyond what our eyes can see, galaxies are dancing, and in their movements, they're writing the next chapter of the universe. Think about the last time you watched two whirlpools form in a stream, their spirals gently tugging at one another until their waters merged into a single, larger flow. That's remarkably similar to how galaxies collide, except on a scale so vast it defies human intuition. These mergers aren't cosmic accidents, they're the universe's way of growing and evolving. In fact, nearly every galaxy we see today, from the majestic spirals to the fuzzy ellipticals, is the product of past collisions. Our own Milky Way bears the scars of ancient mergers, with streams of stars orbiting its outskirts like celestial breadcrumbs left over from smaller galaxies it absorbed billions of years ago. What's truly mind-bending is the timescale involved. While Hollywood might show galaxies smashing together in an instant, real mergers unfold over hundreds of millions of years, sometimes even longer than dinosaurs roamed Earth. Gravity acts as the ultimate puppeteer, gradually pulling galaxies closer until their mutual attraction becomes irresistible. But here's the twist: even as their shapes distort and stars are flung into new orbits, individual stars almost never collide. A galaxy may contain hundreds of billions of stars, but the distances between them are so enormous that they slip past each other like ships in the night. Instead, it's the invisible dark matter, the mysterious substance making up most of a galaxy's mass, that dictates how the dance unfolds, weaving intricate trails of stars and gas in its wake. These collisions don't just reshape galaxies, they reignite them. As clouds of gas and dust compress during a merger, they ignite fireworks of star birth, lighting up the cosmos with newborn stars. Some of the brightest galaxies we observe, starburst galaxies ablaze with young blue stars, are often the result of such violent interactions, yet over time the frenzy settles. Spiral arms blur, and the once distinct galaxies merge into a smooth, elliptical galaxy, their stories forever entwined. By studying these processes, astronomers can read the universe's history like a fossil record, tracing how galaxies grew from tiny seeds in the early cosmos to the giants we see today. And this isn't just ancient history, it's happening right now. Telescopes like Hubble and Webb have captured galaxies in every stage of collision, from the first delicate gravitational tugs to the final shimmering mergers. These observations reveal a universe far more dynamic and interconnected than we once imagined, where even the mightiest galaxies are temporary shapes in an endless cosmic dance. The dance begins almost imperceptibly, two galaxies separated by millions of light years, yet bound by an invisible thread of gravity. As they inch closer, their mutual pull starts working like cosmic sculptors, subtly bending their shapes long before any direct contact. Spiral arms, those elegant, star-filled swirls that define galaxies like our Milky Way, begin stretching into spectacular ribbons of light. These are tidal tails, luminous tendrils of stars and gas flung outward by gravitational forces, forming arcs that can span hundreds of thousands of light years. It's as if the galaxies are reaching out to one another, leaving celestial fingerprints in the void. During these initial encounters, the galaxies might not even collide head-on. Instead, they often glide past each other in a gravitational embrace, each pass warping their structures further. Picture two skaters circling one another, their outstretched arms gradually elongating as they spin. With every close approach, the galaxies lose a bit of energy, drawing them into tighter orbits. This phase can last for hundreds of millions of years, a drawn-out courtship where the galaxies pirouette through space, their forms becoming increasingly distorted. Some develop elaborate bridges of gas between them, while others sprout opposing tidal tails that curve like the horns of a cosmic bull. What's astonishing is how orderly this chaos appears. Despite the tremendous forces at play, the process follows predictable patterns shaped by gravity's unbreakable rules. Computer simulations reveal galaxies bending and twisting in mesmerizing slow motion, their stars tracing out intricate paths like fireflies caught in a gentle breeze. And while the sheer scale of these events is hard to grasp, we've witnessed them firsthand through telescopes. The famous Antennae Galaxies, for example, showcase this early stage perfectly. Their long, intersecting streams of stars resembling the antennae of an insect, hence their name. These luminous arcs are more than just pretty cosmic scenery. They're vital clues helping astronomers decode the physics of galactic interactions. But here's what makes this phase truly remarkable. Even as the galaxies deform, their individual stars remain untouched. The vast emptiness of space means stellar collisions are extraordinarily rare. Instead, it's the galaxy's dark matter halos invisible cocoons of mysterious particles surrounding them that interact most intensely, guiding the visible material like an unseen hand. This interplay between dark and luminous matter determines how the tidal tails form, how sharply the galaxies bend, and ultimately how their merger will unfold. By studying these delicate preludes to collision, scientists gain insights into the hidden architecture of galaxies and the gravitational symphony orchestrating their evolution. And this is just the opening act. As the galaxies continue their gravitational tango, they'll eventually move closer, triggering fireworks of star formation and setting the stage for an even more dramatic transformation. But for now, in this slow-motion approach, we're witnessing one of the universe's most elegant ballets. a dance where the choreography is written in the language of gravity, and the performers are entire galaxies, moving to a rhythm set billions of years ago. As the galaxies draw nearer, their slow-motion dance erupts into a breathtaking spectacle of cosmic transformation. This is the moment when their cores, those dense, brilliant hearts, swing perilously close, locked in a gravitational tug of war that bends space itself. Imagine two whirlpools spinning into one another, their currents twisting and churning as they merge. The galaxy's spiral arms, once elegant and symmetrical, now stretch into chaotic streamers of stars and gas, flung outward like sparks from a firework. But amid this apparent chaos, something extraordinary happens. The violent compression of gas and dust triggers a fireworks display of Starburst. Dense clouds of molecular gas, squeezed by the galaxy's gravitational forces, collapse under their own weight, igniting countless new stars. These stellar nurseries glow with an intense blue hue, the telltale sign of young, massive stars burning fiercely hot. In some merging galaxies, this burst of star formation can be so intense that it outshines the rest of the galaxy combined, a phenomenon astronomers call a starburst. The Antennae Galaxies, for example, are littered with these brilliant blue clusters, each one a testament to the creative power of destruction. And while individual stars rarely collide, the sheer density of gas and dust in these regions ensures that star formation reaches a fever pitch, lighting up the cosmic darkness like a beacon. But the real drama unfolds at the very centers of these galaxies, where supermassive black holes, each millions or even billions of times the mass of our Sun, begin their own spiraling dance. Drawn together by gravity, they orbit one another in an ever-tightening embrace, warping space-time with their immense pull. Eventually, they'll collide in one of the most energetic events in the universe, sending ripples through the fabric of space itself, gravitational waves that echo across the cosmos. Until then, their swirling motion heats surrounding gas to incredible temperatures, creating blazing disks of plasma that shine brighter than all the stars in the galaxy combined. What's mesmerizing about this violent phase is how destruction and creation intertwine. The same forces tearing galaxies apart are also forging new stars and reshaping their structures. Gravity, the ultimate architect, ensures that even in this chaos there's an underlying order. Over time, the galaxy's frantic motions begin to settle. Their once distinct cores merge into a single, larger nucleus, while the expelled stars and gas gradually fall back into a new, more stable configuration. The result, a transformed galaxy, often an elliptical one, its stars now moving in more random orbits, like a swarm of bees instead of a spinning disk. This is the universe's way of recycling. The violent embrace of merging galaxies isn't an end but a rebirth, a cosmic phoenix rising from the turbulence. And while the process takes hundreds of millions of years, telescopes like Hubble and Webb give us snapshots of every stage, allowing us to witness this celestial metamorphosis in real time. From the fiery glow of newborn stars to the eerie calm of a newly merged galaxy, each phase reveals the delicate balance between chaos and order that shapes our universe. The chaos of collision gives way to something quieter but no less profound, a cosmic renaissance. After the gravitational fireworks fade, the merged galaxy begins its slow metamorphosis, settling into a new identity shaped by the violence of its past. What emerges is often an elliptical galaxy, a smooth, featureless glow of stars moving in random orbits, like a swarm of fireflies instead of the orderly spiral arms we started with. These galaxies are the universe's way of turning two distinct stories into a single, grander narrative. Inside this reborn galaxy, the frenetic star formation that once lit up the collision begins to wane. The gas and dust, the raw materials for new stars, have either been burned up in stellar nurseries or blasted away by the relentless winds of supernova explosions. Without fresh fuel, the galaxy's ability to birth stars dims, leaving behind a population of older, redder stars that will shine for billions of years to come. It's a cosmic retirement of sorts, where the galaxy trades youthful exuberance for a more serene, steady glow. But even in this calm, traces of the past remain. Look closely, and you'll find the fingerprints of the merger, ghostly tidal streams of stars arcing through the galaxy's outskirts, like faint brushstrokes on a canvas. These are the remnants of the galaxy's once distinct structures, stretched and scattered by gravity's pull. Some stars, flung free during the collision, now wander alone through intergalactic space, orphans of the cosmic dance. Others gather in unusual clusters, their orbits telling the story of their violent origins. These clues are like cosmic archaeology, helping astronomers piece together the galaxy's turbulent history. And here's the beautiful paradox: while the merger may seem like an ending, it's really a beginning. The new galaxy, though quieter, is often more massive and more stable than its predecessors. It becomes part of a larger cosmic web, its gravity influencing neighboring galaxies and shaping the universe on a grand scale. Even the expelled gas and stars play a role, seeding the intergalactic medium with the building blocks for future generations of galaxies. This is the universe's way of recycling, turning destruction into creation, chaos into order. Every elliptical galaxy we see today, from the faint smudges in deep field images to the giants at the hearts of galaxy clusters, is the product of such mergers. They remind us that in the cosmos, nothing is truly lost, only transformed. And as telescopes peer deeper into space, capturing galaxies in every stage of this process, we're witnessing the timeless dance of destruction and rebirth that has shaped the universe since its earliest days. Dark matter is the unseen choreographer of this cosmic dance, an invisible force holding galaxies together even as they collide and reshape. While we observe the dazzling light shows of stars and gas, it's dark matter that orchestrates the grand movements behind the scenes. Think of it like the hidden framework of a skyscraper. We see the glass and steel, but the building's stability comes from beams we'll never glimpse with our eyes alone. In galactic mergers, dark matter forms vast, diffuse halos around each galaxy, accounting for up to 90% of their total mass. When two galaxies approach, these halos interact first, their gravitational pull creating an invisible scaffold that guides the visible matter into place. Without dark matter, these collisions would play out very differently. Stars and gas clouds, though spectacular, simply don't have enough mass on their own to keep galaxies intact during such violent encounters. They'd scatter like leaves in a storm, leaving behind chaos rather than new galactic structures. But dark matter's relentless gravity acts like cosmic glue, ensuring that even as galaxies twist and stretch, they remain bound together. Computer simulations reveal this vividly. When researchers model collisions without dark matter, galaxies disintegrate, their stars flung into the void. Add dark matter back into the equation, and the familiar, graceful mergers we observe in the universe emerge, tidal tails, starbursts, and all. What's astonishing is how dark matter's influence shapes the aftermath of these collisions. As galaxies merge, their dark matter halos blend into a single, larger halo, creating a gravitational well so deep that displaced stars and gas eventually fall back in, settling into new orbits. This explains why merged galaxies often appear smoother and more spherical. Their stars no longer move in the orderly planes of spiral arms, but instead follow paths dictated by the merged halo's gravity. The Antennae galaxies offer a perfect case study. Their visible gas and stars are entangled in spectacular arcs, but simulations show their dark matter halos already overlapping, silently herding the luminous material toward its eventual fate. Yet for all its importance, dark matter remains one of astronomy's greatest mysteries. We detect it only through its gravitational effects, like a shadow moving behind a curtain. Its particles, whatever they are, don't emit, absorb, or reflect light, making direct observation impossible with current technology. This invisibility adds a layer of poetry to galactic collisions. The most massive player in the dance is one we'll never see. Future telescopes and experiments aim to uncover dark matter's true nature, but for now, its role in shaping galaxies stands as a testament to the hidden forces weaving the universe together. And this unseen influence isn't just a cosmic curiosity, it's a reminder of how much we have yet to discover. Every galactic collision we observe, every simulation we run, brings us closer to understanding the invisible architecture of the cosmos. The dance of galaxies is, in truth, a dance of dark matter, with stars and gas merely following its lead. As we peer deeper into these mergers, we're not just witnessing the evolution of galaxies, we're decoding the hidden rules of the universe itself. Among all the galactic collisions witnessed across the cosmos, few capture the imagination like the Antenna Galaxies. This pair, officially known as NGC 4038 and NGC 4039, has become a textbook example of mid-collision chaos, a snapshot of celestial transformation frozen in time. Located about 60 million light-years away in the constellation Corvus, these galaxies earned their name from the spectacular twin arcs of stars stretching far into space, resembling insect antennae caught mid-swing. But these luminous tendrils are more than just a striking visual. They're a direct result of the galaxy's gravitational tug of war, a cosmic fingerprint revealing the forces at work. Hubble's gaze has peeled back the layers of this merger, exposing a fireworks display of Starburst unlike anything in our galactic neighborhood. Compressed clouds of gas and dust, squeezed by the collision's violence, have ignited into thousands of brilliant blue star clusters, some containing stars just a few million years old. These clusters glow with an intensity that outshines their surroundings, marking regions where the galaxy's raw material is being forged into new suns at a frenzied pace. Yet amid this stellar nursery, there's destruction too. Shockwaves from supernovas, the explosive deaths of massive stars, ripple through the gas clouds, carving cavities and triggering further star formation in a self-perpetuating cycle. The antennae are a living laboratory of creation and destruction, where every process feeds into another. What makes this collision so special is its timing. The antennae are caught in what astronomers call the starburst phase, the peak of stellar rebirth. Simulations suggest these galaxies first brushed past each other a few 100 million years ago, their mutual gravity stretching their spiral arms into those iconic tidal tails. Now, as they swing back for a second, closer encounter, their cores are beginning to intertwine, setting the stage for an eventual merger into a single elliptical galaxy. This interim period, where the galaxies are neither fully separate nor fully merged, offers a rare chance to study how such collisions unfold. We're witnessing the universe's creative power in overdrive, where chaos breeds new structure. And here's where it gets personal. The antennae serve as a cosmic mirror, reflecting what awaits our own Milky Way when it meets Andromeda. While that collision is billions of years away, the physics remains the same: spiral arms distorting, gas clouds collapsing into stars, and tidal streams lighting up the darkness. By studying the antennae, we're essentially fast-forwarding through our galaxy's future. Already, astronomers have spotted similarities, from the distribution of young star clusters to the way dark matter guides the dance. The antennae remind us that galaxies aren't static islands but dynamic beings, constantly evolving through encounters we're only beginning to understand. But perhaps the most humbling lesson lies in the timescales. The antennae's merger will take longer than all of human history, stretching across epochs when entire species might rise and fall on distant worlds. Yet to the universe, this is just a fleeting moment, one of countless collisions shaping the cosmic web. Through telescopes, we're granted a front-row seat to this slow-motion spectacle, where gravity writes its poetry in starlight and gas, and where destruction always carries the seeds of new beginnings. While the Antennae galaxies show us the fireworks of a mid-collision merger, the mice galaxies offer a glimpse into the opening act, a slower, more delicate gravitational courtship. Officially known as NGC 4676, this pair lies about 300 million light-years away in the constellation Coma Berenices, their long, thread-like tails stretching far into the void like celestial brushstrokes. These tails, each over 100,000 light-years long, aren't just debris, they're the galaxy's very essence unraveling under the relentless pull of gravity. What makes the mice so fascinating is their stage in the collision process. Unlike the antennae, which are already deeply intertwined, the mice are in the early phases of interaction, their cores still distinct but their outer regions already warping into these spectacular streams. Imagine two dancers spinning close enough to grasp each other's hands. Their bodies remain separate, but their outstretched arms stretch and blur with motion. That's what's happening here on a galactic scale. The mica's tails are made of stars, gas, and dust stripped from their parent galaxies, flung outward by tidal forces during their first close pass. This stretching reveals a critical truth about galaxies. They're not the rigid, unchanging islands we once imagined. Instead, they're fluid and dynamic, their shapes malleable under gravity's influence. The mica's slender tails, visible in stunning detail through telescopes like Hubble, are proof of this cosmic plasticity. Some of the stars in those tails will never return to their original galaxies. They'll wander forever in intergalactic space, a silent testament to the encounter's violence. Others may eventually fall back, drawn in by the merged galaxy's growing gravity. But the real magic lies in what these tails tell us about dark matter. The way they curve and lengthen matches computer simulations almost perfectly, but only if we account for the invisible halos of dark matter surrounding each galaxy. Without those halos, the tails would look entirely different, their shapes less pronounced and their stars more scattered. The mice, then, aren't just a pretty cosmic snapshot. They're a natural experiment, helping astronomers test theories about how dark matter shapes galactic encounters. And there's something hauntingly beautiful about their asymmetry. While both galaxies sport tails, one is longer and more pronounced, likely because the galaxies aren't identical in mass or structure. This lopsidedness mirrors the imperfections of real cosmic collisions, where no two galaxies meet on perfectly equal terms. Over hundreds of millions of years, the mice will continue their dance, their tails growing even longer before eventually falling back as the galaxies merge into a single, new structure. By then, their elegant streams will have faded, absorbed into the glow of the newly formed galaxy, but for now, they remain one of the universe's most striking examples of gravity's artistry. What's remarkable is that we're seeing this event not as it unfolds, but as it appeared 300 million years ago, around the time Earth's first forests were taking root. The light now reaching our telescopes began its journey long before humans existed, a reminder of how these slow-motion dramas transcend our fleeting sense of time. The mice galaxies challenge us to think on cosmic scales, where a single galactic embrace can span epochs, and where destruction and creation are two sides of the same celestial coin. Right now, the Andromeda Galaxy appears as a faint smudge in our night sky, a quiet neighbor drifting toward us at 250,000 miles per hour. But in 4.5 billion years, that distant glow will become impossible to ignore as it swells into a breathtaking celestial spectacle. The Milky Way and Andromeda, two spiral giants each harboring hundreds of billions of stars, are destined for a gravitational embrace that will reshape our galactic neighborhood forever. Computer simulations reveal the dance in stunning detail. Initially, Andromeda will loom larger in our sky, its spiral arms twisting as tidal forces stretch both galaxies into spectacular arcs. Their first close pass won't be a direct collision but a graceful swing by, like two dancers circling one another before clasping hands. Over millions of years, gravity will draw them back together, their cores pirouetting in ever tighter orbits. Stars from both galaxies will be flung into new trajectories, our own solar system likely hurled outward, though still bound to the merging pair. The sheer vastness of space means most stars will glide past one another unscathed, like grains of sand missing each other in a hurricane. As the galaxies intertwine, the night sky will transform beyond recognition. Andromeda's disk will sprawl across the heavens, its dust lanes and star clusters visible to the naked eye. Then, as their cores finally merge, a fireworks display of Starburst will ignite gas clouds compressed by the collision, blazing with newborn stars. But this frenzy won't last. After nearly 10 billion years of slow-motion choreography, the spiral's distinct structures will blur into a single, elliptical galaxy astronomers nicknamed Milky-Way. Gone will be the Milky Way's familiar disk, in its place a golden haze of older stars orbiting in all directions. What's striking is how ordinary this event is on a cosmic scale. Most galaxies we see today, including many ellipticals, are the products of past mergers. Our own Milky Way bears scars from ancient collisions, its outer halo littered with stellar streams from smaller galaxies it absorbed long ago. Even now, it's cannibalizing the Sagittarius Dwarf spheroidal galaxy, a process repeating across the universe. These mergers aren't accidents but the universe's way of growing, a cycle as natural as rivers carving canyons. Yet this future collision holds a humbling lesson. We often think of galaxies as eternal, but they are as fleeting as the stars within them. The Milky Way and Andromeda have existed for over 10 billion years, yet their merger will erase their spiral identities in a cosmic blink. For any civilization witnessing the event, the sky will tell a story of impermanence, a reminder that even the grandest structures are threads in a tapestry of constant change. And somewhere, in the glow of Milky-Way's combined light, there may still be planets orbiting stars, their skies alight with the legacy of two galaxies that once danced apart. While the colossal mergers of spiral galaxies capture our imagination with their fireworks, the quieter absorption of dwarf galaxies tells an equally important story, one of steady, incremental growth. Picture a bustling city expanding not through dramatic upheavals, but by gradually absorbing nearby towns. That's how galaxies like our Milky Way have built themselves over billions of years, quietly pulling in smaller neighbors and weaving their stars into the galactic fabric. These minor mergers may lack the visual spectacle of colliding giants, but they're the universe's preferred method of galactic construction, happening far more frequently than their dramatic counterparts. Take the Sagittarius Dwarf spheroidal galaxy, a tiny satellite of the Milky Way currently being torn apart by our galaxy's gravity. As it orbits, tidal forces strip away its stars, scattering them into shimmering streams that wrap around the Milky Way like celestial ribbons. These streams, visible through powerful telescopes, are more than just pretty cosmic debris. They're forensic evidence of the Milky Way's cannibalistic past. Astronomers have identified at least a dozen such stellar streams, each the remains of a dwarf galaxy or star cluster consumed long ago. The most famous, the Gaia Sausage Stream, is the remnant of a dwarf galaxy that collided with the Milky Way around 8 to 10 billion years ago, its stars now scattered across our galaxy's halo in a distinct orbital pattern. What's fascinating is how these minor mergers differ from their colossal cousins. Without the violent bursts of star formation or dramatic tidal tails, dwarf galaxy accretions are slow, methodical affairs. The smaller galaxy stars are gradually dispersed into the larger galaxy's halo, while its dark matter halo, if it had one, merges seamlessly with the hosts. Gas from the dwarf may trickle into the larger galaxy's disk, fueling subtle waves of new star formation. These events are so gentle that they often leave the larger galaxy's structure intact, its spiral arms undisturbed. It's the cosmic equivalent of adding a sprinkle of new ingredients to a simmering stew, each small addition enriching the flavor without overwhelming the pot. Yet these quiet mergers are far from insignificant. Studies suggest that up to half of the Milky Way's outer halo stars were stolen from dwarf galaxies, making them essential contributors to our galaxy's growth. Even now, the Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, is orbiting the Milky Way, destined to eventually merge with us in a few billion years. These hierarchical mergers, where small structures combine into larger ones, are how galaxies assemble themselves across cosmic time. Every major galaxy we see today is the product of countless such small-scale unions, layered like the rings of a tree trunk. The beauty of these minor mergers lies in their accessibility. Unlike the rare, dramatic collisions of spiral galaxies, dwarf galaxy accretions are happening all around us, offering astronomers a real-time laboratory to study galactic evolution. By mapping the motions and compositions of stolen stars, researchers can reconstruct the Milky Way's history of galactic conquests, a fossil record written in starlight. And as telescopes grow more powerful, they're revealing even fainter streams, hinting at mergers so ancient their stars have nearly faded into the galactic background. These quiet cosmic dramas remind us that galaxies aren't just defined by their most violent encounters, but by the slow, persistent accumulation of smaller pieces, a testament to the universe's patience in building its grandest structures. When galaxies collide, they don't just rearrange their stars, they ignite a celestial fireworks show of stellar birth. Starburst galaxies are the universe's way of turning chaos into creation, where the violent compression of gas during collisions sparks frenzied waves of star formation. Take the Cigar Galaxy, officially known as M82, a cosmic powerhouse glowing so brightly in infrared light that it outshines nearly every other galaxy in its neighborhood. This brilliance isn't just for show, it's the signature of countless young stars being born at a rate 10 times faster than in our own Milky Way. Hidden behind veils of dust, these stellar nurseries radiate heat that telescopes like Hubble and Webb can detect, revealing the hidden turmoil beneath. What makes Starburst so extraordinary is their intensity and brevity. Like a match struck in a windstorm, these episodes burn fiercely but briefly, cosmically speaking. A typical starburst might last only a few tens of millions of years, a mere blink compared to a galaxy's multi-billion-year lifespan. The reason? These galaxies are essentially burning through their fuel reserves at an unsustainable pace. As gas clouds collapse under the weight of their own gravity, they fragment into dense cores, each igniting into a new star. But this frenzy can't last forever. Supernovas, the explosive deaths of the most massive stars, soon blast away remaining gas, while fierce stellar winds sweep it out into intergalactic space. The result is a galaxy that eventually exhausts itself, its star-forming factories shutting down as quickly as they flared to life. Yet within this short-lived chaos lies a deeper cosmic purpose. Starbursts are nature's way of recycling galactic material on a grand scale. The massive stars born in these eruptions live fast and die young, enriching their surroundings with heavy elements forged in their cores. When they explode, they scatter oxygen, carbon, and iron into the surrounding gas, ingredients essential for future stars, planets, and even life. In this way, starburst galaxies act as cosmic crucibles, transforming primordial hydrogen into the building blocks of complexity. The Cigar Galaxy isn't alone in this spectacle. NGC 253, the Silver Dollar Galaxy, gleams with similar ferocity, its spiral arms alight with clusters of blue supergiants. Even the Antenna Galaxies, locked in their slow-motion collision, host vast regions where starburst activity lights up the merging chaos. What ties these galaxies together is their shared trigger, the gravitational upheaval of interactions. Whether it's a full-blown merger or a close encounter, the compression of gas is the common spark that ignites the fire. But here's the twist: not all starbursts require collisions. Some galaxies, like Messier 61, seem to flare up from internal processes, their spiral arms convulsing with star birth without any obvious external trigger. This suggests that while collisions are one path to starbursts, they're not the only one. Turbulence from supermassive black holes, density waves rippling through galactic disks, or even the accretion of fresh gas from intergalactic space can all push a galaxy into overdrive. The universe, it seems, has multiple ways to light the fuse. What's humbling is realizing how much we owe to these brief, brilliant episodes. The heavy elements in our own bodies, the iron in our blood, the calcium in our bones, were likely forged in the hearts of stars born during ancient starbursts. These violent, short-lived events are the universe's way of turning simplicity into complexity, chaos into structure, and as telescopes peer deeper into the cosmos, capturing starbursts in galaxies billions of light-years away, we're witnessing a process that's as old as the universe itself, a reminder that creation often wears the mask of destruction. At the heart of every galaxy lies a gravitational monster, a supermassive black hole millions or even billions of times heavier than our Sun. When galaxies collide, these cosmic titans are drawn together, beginning a slow, inevitable dance toward catastrophe. Picture two whirlpools spinning ever closer in a vast ocean, their currents intertwining as they spiral toward a final, violent embrace. That's the fate awaiting these black holes, but the journey there is anything but simple. Initially separated by thousands of light-years, the black holes orbit each other in a cosmic waltz that can last for hundreds of millions of years. Their immense gravity tugs at the surrounding stars and gas, creating a chaotic environment where friction gradually saps their orbital energy. Like marbles circling a drain, they lose speed with each pass, drawing nearer in a process astronomers call dynamical friction. During this phase, the black holes carve out vast cavities in the galactic core, flinging stars away like cosmic pinballs and heating nearby gas to millions of degrees. Telescopes have spotted galaxies where this dance is underway, their cores glowing unusually bright as matter spirals into the dueling black holes, releasing torrents of X-rays. But the real spectacle begins when the black holes close within a few light-years of each other. At this distance, their gravitational influence becomes so dominant that they form a binary system, orbiting so tightly that a single lap might take just a few hundred years. Here, the final stages of the merger unfold with breathtaking precision. Einstein's theory of general relativity predicts that as the black holes spiral inward, they radiate energy in the form of gravitational waves, ripples in the fabric of space-time itself. These waves carry away orbital energy, hastening the black hole's final plunge. In the last moments before collision, they whirl around each other thousands of times per second, distorting space-time like a blender churning the cosmos. The merger itself is a violent crescendo. When the black holes finally collide, they release more energy in gravitational waves than all the stars in the observable universe combined emit as light during the same instant. For a fraction of a second, the merged black hole vibrates like a struck bell, its surface rippling as it settles into a new, more massive form. This event, though invisible to traditional telescopes, leaves an indelible mark on the universe. Gravitational wave detectors like LIGO and Virgo are tuned to catch these distant tremors, which stretch and compress space by less than the width of an atom as they pass through Earth. What's astonishing is how hidden these events remain. Unlike starbursts or tidal tails, black hole mergers play out behind thick curtains of dust and gas, their light swallowed by the very gravity they generate. Only through gravitational waves and the occasional burst of high-energy radiation can we glimpse these cosmic showdowns, yet their impact is profound. By studying them, astronomers trace how supermassive black holes grow, from seeds in the early universe to the behemoths we see today. Each merger is a missing piece in the puzzle of galactic evolution, revealing how the universe builds its most enigmatic structures. And there's a tantalizing possibility lurking in these collisions. Some theories suggest that under the right conditions, the recoil from a black hole merger could be so powerful it kicks the newborn black hole clear out of its host galaxy, sending it careering into intergalactic space at millions of miles per hour. Imagine a supermassive black hole alone in the void, a relic of a galactic collision that reshaped the cosmos. While rare, these rogue black holes would be ghosts of mergers past, drifting silently through the darkness, their origins written in the gravitational waves they left behind. Detecting these mergers isn't just about witnessing cosmic violence, it's about decoding the universe's hidden language. Every ripple in space-time carries information about the black hole's masses, spins, and even the environment where they merged. Future observatories like the space-based LISA mission will listen for these waves with unprecedented precision, opening a new window into the most energetic events since the Big Bang. What they reveal could rewrite our understanding of how galaxies and the black holes at their hearts shape the cosmos. For now, these dueling giants remind us that even in the vast stillness of space, change is constant. Galaxies collide, black holes merge, and space-time itself shudders under the force of these encounters. And somewhere, in the darkness between the stars, another pair of supermassive black holes is beginning its slow dance toward oblivion, a dance that began billions of years ago and will echo across the universe long after we're gone. Galactic cannibalism might sound like the plot of a cosmic horror story, but it's actually the universe's way of growing galaxies through a slow, methodical feast. Unlike the dramatic collisions of spiral galaxies we often picture, this process is subtler, more like a giant redwood absorbing nutrients from the soil than a violent explosion. The Milky Way itself is a prime example of this phenomenon, currently digesting the Sagittarius Dwarf spheroidal galaxy, which orbits our galactic home like a moon around a planet. Over billions of years, our galaxy's immense gravity has been pulling this dwarf galaxy apart, stretching its stars into a shimmering river of light that wraps around the Milky Way like a celestial serpent. What makes these events so fascinating is their deceptive gentleness. Without the fireworks of starbursts or the spectacular tidal tails seen in major mergers, galactic cannibalism unfolds almost imperceptibly. The Sagittarius Dwarf, for instance, has been losing stars for eons, its material gradually blending into the Milky Way's outer halo. Yet this slow dismantling leaves forensic evidence. Streams of stars tracing the dwarf's orbital path, their motions and chemical compositions betraying their foreign origins. These stellar rivers, invisible to the naked eye but detectable through telescopes, are like breadcrumbs leading us back through cosmic history. They reveal that the Milky Way didn't form in isolation but grew by assimilating smaller neighbors, one bite at a time. This process isn't unique to our galaxy. Across the universe, large galaxies act as gravitational anchors, drawing in smaller companions and incorporating their stars, gas, and even dark matter. The Andromeda Galaxy, our nearest spiral neighbor, shows similar scars of past meals, its outskirts littered with the remnants of devoured dwarf galaxies. Even elliptical galaxies, those smooth, featureless giants, likely grew to their enormous sizes through countless acts of galactic cannibalism. Their random stellar orbits a testament to their violent dining history. But here's the twist: while these mergers may seem destructive, they're ultimately creative acts. The stolen stars don't vanish. They become building blocks for new galactic structures. Gas stripped from dwarf galaxies can sink toward the larger galaxy's center, fueling future star formation. Dark matter from the consumed galaxy blends into the host's halo, strengthening its gravitational grip. In this way, galactic cannibalism isn't just about destruction, it's about recycling matter on a cosmic scale, ensuring nothing in the universe goes to waste. The Sagittarius dwarf's fate holds special significance because it's happening right now, offering astronomers a front-row seat to the process. Its tidal streams, first mapped in detail by the Sloan Digital Sky Survey, show how gravity stretches and distorts a galaxy as it's pulled apart. Some of its stars have already been fully incorporated into the Milky Way's halo, while others remain in delicate filaments that may persist for billions of years. This ongoing digestion gives us crucial insights into how galaxies assemble themselves over time, not through sudden, dramatic collisions, but through a slow, persistent accumulation of smaller pieces. Perhaps most remarkably, these events remind us that no galaxy is an island. The universe operates through connection and interaction, with even the mightiest galaxies owing their existence to countless smaller mergers. Every time we look up at the Milky Way's starry band, we're seeing the legacy of these cosmic meals, a galactic tapestry woven from the threads of devoured neighbors. And somewhere out there in the dark, another dwarf galaxy may already be falling toward us, destined to become part of our galaxy's ever-growing story. The vast emptiness of space offers an unexpected gift during galactic collisions: safety for planets. While galaxies may seem packed with stars when we gaze at their glittering disks, the reality is staggeringly sparse. On average, stars in a galaxy like the Milky Way are separated by about 4 light-years. That means if our sun were the size of a grapefruit in Los Angeles, the nearest star would be another grapefruit in Chicago. This incredible emptiness ensures that when galaxies collide, stars and their orbiting planets almost never come close enough to disrupt each other's gravitational bonds. Imagine standing on a world caught in the Milky Way-Andromeda merger. Over billions of years, your night sky would transform dramatically. New constellations would emerge as foreign stars from Andromeda mingle with familiar ones, their combined light painting ever-shifting patterns. Yet through it all, your planet's orbit around its sun would remain as stable as Earth's is today. The forces binding a solar system together are so localized that even the gravitational turmoil of colliding galaxies can't easily break them. It's like being in a car on a bumpy road. No matter how rough the ride, the passengers inside stay firmly in their seats. But there's a caveat: radiation. While direct collisions are unlikely, the starbursts triggered by galactic mergers flood space with intense ultraviolet light and X-rays from newborn massive stars. For planets with thin atmospheres, this could mean trouble. over time, the increased radiation might erode away protective layers, leaving surfaces exposed to harsh cosmic rays. Earth-like worlds with strong magnetic fields might fare better, their invisible shields deflecting the worst of the bombardment. The habitability of any given planet would depend on a delicate balance, its distance from starburst regions, the strength of its magnetic field, and the resilience of its atmosphere. For civilizations evolving in the aftermath of a merger, the changes would be both subtle and profound. Early astronomers might notice strange new stars appearing over generations, their motions tracing out the slow dance of merging galaxies. Later generations would witness the full spectacle, the once distinct band of the Milky Way blending with Andromeda's glow, creating a sky ablaze with stars in every direction. Yet even amid this celestial upheaval, the rhythms of daily life could continue uninterrupted. The universe's scale ensures that while galaxies may collide, the worlds within them remain islands of stability, their fates determined more by their local environment than the cosmic chaos around them. This cosmic resilience offers a humbling perspective. The same emptiness that makes the universe feel lonely also protects it from constant catastrophe. Planets and any life they might harbor can endure galactic collisions not through sheer toughness, but because space is so unthinkably vast. As the Milky Way and Andromeda merge, countless solar systems will carry on undisturbed, their stories continuing across the eons. The universe may reshape itself on the grandest scales, but in the quiet neighborhoods around stable stars, life, if it exists, could persist, adapting to new skies without ever losing its home. To witness the universe in its youth is to watch a cosmic construction site in overdrive, a time when galaxies were smaller, packed tighter, and collisions happened with startling frequency. The early universe was a place of constant upheaval, where these frequent mergers laid the foundations for the grand spiral and elliptical galaxies we see today. Unlike the carefully spaced galactic neighborhoods of the modern cosmos, where collisions are rare events spaced billions of years apart, the young universe was a crowded, chaotic place. Galaxies formed closer together, their mutual gravitational pull drawing them into near-constant interactions. This was the era of the first great galactic mergers, collisions that didn't just reshape individual galaxies but fundamentally built the universe as we know it. When two small, gas-rich galaxies smashed together in those early epochs, they didn't just combine their stars, they ignited explosions of star formation that flooded the cosmos with the first heavy elements. Elements like carbon, oxygen, and iron, the building blocks of planets and life itself, were forged in the hearts of these early stars, then scattered into space by supernovas. Each collision was a crucible, turning the pristine hydrogen and helium of the young universe into something richer and more complex. The James Webb Space Telescope has given us an unprecedented window into this formative era. Peering back over 13 billion years, its infrared eyes capture galaxies in the throes of violent mergers, their shapes distorted by gravitational forces we can now study in detail. Some of these early galaxies look nothing like the neat spirals and smooth ellipticals we're familiar with. Instead, they appear as misshapen blobs, racked by the turbulence of their collisions. Yet within this chaos we see the seeds of order. These mergers didn't just destroy, they built. Small proto-galaxies smashing together formed larger structures, which in turn collided to create even bigger galaxies. It was a bottom-up process, with each merger adding another layer to the cosmic web. What's astonishing is how quickly this happened. Within just a few 100 million years of the Big Bang, a blink in cosmic time, the first galaxies were already merging, their collisions shaping the universe's large-scale structure. Some of these early mergers were so violent they may have triggered quasars, supermassive black holes at the hearts of galaxies, feeding on the gas stirred up by the collisions and shining brighter than entire galaxies. These beacons of light, visible across billions of light years, are some of our best clues to understanding how the first galaxies grew. Yet for all their violence, these early mergers followed a pattern. Computer simulations show that while individual collisions were chaotic, the overall trend was toward structure. Just as streams merge into rivers and rivers into oceans, small galaxies merged into larger ones, their combined gravity pulling in even more neighbors. This process, called hierarchical merging, is why we see such a variety of galaxy shapes today. The spirals, the ellipticals, the irregulars, each is the product of a unique merger history, a cosmic fingerprint shaped by billions of years of collisions. And the legacy of these early mergers isn't just in the galaxies they built. The heavy elements they scattered became the raw material for future generations of stars, planets, and perhaps even life. Every atom of oxygen in your lungs, every speck of iron in your blood, was once part of a star born in one of these ancient galactic collisions. The universe we see today, with its majestic galaxies and diverse planets, is the product of a chain of mergers stretching back to the dawn of time. The James Webb Space Telescope is now allowing us to watch this story unfold in real time, or rather, in deep time. Each image it captures is a snapshot of the universe's childhood, showing us how today's galactic giants were once just clusters of young stars colliding and growing in the darkness. What was once theoretical is now visible, the universe building itself one merger at a time. Gas is the invisible sculptor of galactic collisions, a force both delicate and violent, shaping the destiny of merging galaxies. While stars glide past each other like ships in the night during these encounters, gas clouds slam together with tremendous force, triggering chain reactions that can light up the cosmos. Picture two giant clouds of interstellar gas, each trillions of miles across, colliding at hundreds of miles per second. The shock waves ripple through them like thunder, compressing pockets of gas until they collapse under their own gravity, igniting the fires of newborn stars. This is why merging galaxies often glow with such intense blue light. It's the signature of countless young, massive stars burning hot and fast, their brilliance outshining everything else in the galaxy. But gas doesn't just create stars during mergers, it also faces catastrophic expulsion. The very stars it births soon rebel against it. Massive stars live short, violent lives, ending in supernova explosions that blast shockwaves through surrounding gas clouds. These stellar detonations act like cosmic winds, pushing gas outward at incredible speeds, sometimes even ejecting it entirely from the galaxy. In extreme cases, galaxies can lose up to 90% of their star-forming material this way, leaving them gas-poor and unable to birth new stars. It's a cosmic irony. The gas that fuels starbursts also sows the seeds of its own destruction. Meanwhile, some gas takes a different path, one that leads straight into the abyss. As galaxies merge, their chaotic gravitational dance funnels gas toward their central supermassive black holes. This infalling gas doesn't go quietly. As it spirals inward, friction heats it to millions of degrees, creating blazing disks of plasma that glow brighter than all the galaxy's stars combined. These active galactic nuclei, or AN, can outshine entire galaxies for millions of years, their radiation flooding space with enough energy to influence star formation thousands of light years away. Some theorists believe this feedback mechanism, where black holes regulate their own growth by heating or expelling gas, might explain why we don't see galaxies much larger than those observed. The black holes, in a sense, shut off their own food supply. The fate of a merged galaxy hinges on this delicate gas balance. If enough gas remains after the collision, either because the merger was gentle or the galaxies were especially gas-rich. The new galaxy may continue forming stars for billions of years, perhaps even retaining its spiral structure. But if too much gas is blown away or consumed by the black hole, the galaxy enters a twilight state astronomers call red and dead. Its remaining stars age without replacement, their light reddening over time as the galaxy's once vibrant star-forming factories fall silent. The Milky Way and Andromeda's future merger offers a fascinating case study. Both galaxies have already used up much of their original gas reserves, so their collision might not produce the spectacular starbursts seen in younger mergers. Instead, they could form a quiet, elliptical galaxy, a golden haze of aging stars with little gas left to spark new stellar generations. Yet gas isn't just a passive player, it's also an archive. The chemical composition of gas clouds records a galaxy's entire history. Each generation of stars fuses lighter elements into heavier ones, and when those stars explode, they enrich surrounding gas with metals, as astronomers call all elements heavier than hydrogen and helium. By studying the gas in merging galaxies, researchers can trace past star formation episodes. Much like tree rings reveal years of growth, some gas clouds in the Antennae galaxies, for example, show higher metal content than others, evidence that certain regions have undergone more cycles of star birth and death. This chemical fingerprinting allows astronomers to reconstruct merger timelines, revealing which parts of a galaxy collided first and how the chaos unfolded. What's remarkable is how long this gas-driven drama can last. While the initial collision might take a few 100 million years, the aftermath, gas settling, star formation flickering out, black holes finishing their feast, can stretch for billions of years. Telescopes like ALMA, which observe cold gas in radio wavelengths, have spotted galaxies where merger-triggered starbursts occurred billions of years ago, yet faint wisps of gas still linger, tracing ghostly orbits around the merged core. These remnants are like smoke after a fireworks display, the last traces of a cosmic spectacle that reshaped an entire galaxy. And this isn't just about distant galaxies, it's about us. The gas in our Milky Way today, the material that might one day form new solar systems, carries the chemical legacy of ancient mergers. Every atom of oxygen in Earth's atmosphere, every carbon molecule in our bodies, was forged in stars born from colliding gas clouds billions of years ago. Galactic mergers, for all their destructive grandeur, are ultimately creative acts rearranging gas into new stars, new planets, and perhaps new possibilities for life. As we study these collisions across the cosmos, we're not just watching galaxies evolve, we're tracing the journey of the very elements that make our existence possible. Amid the chaos of colliding galaxies, something extraordinary can emerge. Not just destruction, but new beginnings. When titanic gravitational forces stretch and shred galaxies, they sometimes leave behind more than just debris. Like celestial sparks cast off from a cosmic fire, tidal dwarf galaxies form from the displaced stars and gas flung outward during these violent encounters. These aren't your typical galaxies. Unlike their primordial cousins, which condensed from pristine gas clouds in the early universe, tidal dwarfs are born from the wreckage of collisions, making them cosmic underdogs with a fascinating secret: they contain almost no dark matter. Picture this as two galaxies swing past each other. Their gravitational pull acts like a slingshot, hurling streams of stars and gas into intergalactic space. Most of this material will eventually fall back into the merged galaxy, but sometimes, if conditions are just right, these orphan clouds can collapse under their own gravity, forming a new, tiny galaxy. The process mirrors how eddies and whirlpools form in a river's current: small, self-contained structures spinning off from larger flows. The Antennae galaxies offer a stunning real-world example, with at least 4 tidal dwarf candidates glowing amid their tangled tidal tails. What makes these galaxies so intriguing is what they lack: dark matter, the invisible scaffolding that makes up most of a normal galaxy's mass doesn't get pulled into these tidal streams the way visible matter does. That's because dark matter, unaffected by the friction and pressure that shape gas and stars, remains more diffusely distributed in the original galaxy's halos. When astronomers measure the rotation speeds of tidal dwarfs, they find something startling: these galaxies rotate exactly as expected based on their visible mass alone, with no need for dark matter to explain their motions. It's a crucial clue helping scientists distinguish between dark matter's influence and the behavior of ordinary matter. This dark matter deficit isn't just a curiosity, it's a powerful tool for testing our theories of galaxy formation. Primordial dwarf galaxies, which formed in the early universe, are dominated by dark matter. Their stars move so fast that without vast amounts of invisible mass holding them together, they'd fly apart. Tidal dwarfs, by contrast, are like cosmic control experiments, galaxies made purely from the normal matter we can see, letting astronomers study how gas and stars behave without dark matter's confounding effects. The differences between these two types of small galaxies are helping researchers refine models of how dark matter interacts with ordinary matter across cosmic time. Yet these tiny galaxies face an uncertain future. Without dark matter's gravitational anchor, tidal dwarfs are more vulnerable to disruption. Some may be torn apart by the very galaxies that birthed them, their stars scattering into the galactic halo. Others might endure for billions of years, quietly orbiting their parent galaxies as living fossils of ancient collisions. A few could even become the seeds for future galactic growth, captured by other passing galaxies and absorbed into their structures. Each possibility offers a window into the life cycles of galaxies, showing how destruction and creation are intertwined on cosmic scales. The study of tidal dwarfs also holds clues to one of astronomy's biggest puzzles: the missing satellites problem. Computer simulations of dark matter predict that large galaxies like the Milky Way should be surrounded by hundreds of small dark matter clumps, yet we observe far fewer dwarf galaxies than expected. Tidal dwarfs complicate this picture as they form through entirely different processes than primordial dwarfs. By learning to distinguish between these two populations, astronomers are getting closer to understanding whether the mismatch is due to problems with our dark matter models, or simply because many predicted dwarfs are too faint to see. Every time telescopes spot a new tidal dwarf galaxy, it's like finding a message in a bottle from a galactic collision that occurred billions of years ago. These fragile structures carry information about the forces that shaped them, the composition of their parent galaxies, and the behavior of matter under extreme conditions. In their own quiet way, they're rewriting our understanding of how galaxies evolve, not just through grand mergers, but through the subtle interplay of gravity, gas, and the invisible architecture of the cosmos. And somewhere out there, in the tidal tails of colliding giants, new dwarfs may be taking shape even now, their birth heralding the next chapter in the universe's endless story of transformation. Behind the thick dust veils of colliding galaxies lies one of the universe's best-kept secrets: ultraluminous infrared galaxies, or ULIRG. These cosmic powerhouses shine hundreds of times brighter than our Milky Way, yet their light doesn't reach us in visible wavelengths. Instead, their brilliance is trapped behind curtains of dust, heating those particles until they glow fiercely in infrared, a form of light invisible to our eyes but screaming with energy to telescopes like Spitzer and Webb. What makes these galaxies extraordinary isn't just their luminosity but the engines behind it. a perfect storm of star formation and voracious black holes, both unleashed by the chaos of galactic collisions. When two gas-rich galaxies merge, their interstellar clouds slam together with such force that they ignite bursts of star formation at rates hundreds of times faster than normal. But unlike starbursts in visible light, where newborn stars illuminate their surroundings, ULUG trap that light. Dust clouds, thick enough to block entire constellations, absorb the starlight, re-radiating it as infrared heat. It's like muffling a supernova inside a cosmic pillow. The energy is still there, just transformed. The resulting glow can outshine all the stars in the Milky Way combined, turning these galaxies into infrared beacons visible across billions of light years. Yet starbursts alone can't explain ULUG's extreme luminosity. At their hearts, another monster stirs a supermassive black hole gorging on gas funneled inward by the merger's turbulence. As material spirals toward the black hole, friction heats it to millions of degrees, creating a blazing accretion disk that can rival the starburst's energy output. In some ULUG, this black hole activity is so intense it produces powerful jets and winds, carving cavities in the surrounding gas and shaping the galaxy's evolution. The interplay between these two power sources, stellar birth and black hole feeding, creates a feedback loop that defines ULUG's brief but spectacular lives. This phase doesn't last. The same dust that hides ULUG's brilliance also seals their fate. Over time, fierce stellar winds and black hole outbursts blow away the obscuring dust, like a gale stripping fog from a mountaintop. What emerges is often a quasar, a galaxy whose now exposed black hole shines with unobstructed fury, its radiation flooding space with visible and ultraviolet light. ULUG, then, are cosmic chrysalides, a transitional stage where galaxies transform from dust-shrouded prodigies to radiant quasars, their hidden energy finally unleashed. The ARP 220 system, one of the nearest ULUG, offers a stunning case study. Located about 250 million light-years away, this merging pair glows with the infrared light of over 1 trillion suns. High-resolution images reveal twin cores, the remnants of the original galaxy's centers, surrounded by a maelstrom of dust and gas. Radio telescopes have detected over 200 supernova remnants in ARP 220, evidence of the starburst's ferocity, while X-ray observations hint at a hidden black hole devouring its surroundings. This single system encapsulates the ULUG phenomenon, a fleeting firestorm of creation and destruction that reshapes galaxies forever. What's humbling is realizing how much of the universe's evolution happens behind this dusty veil. Before telescopes could see in infrared, ULUG were nearly invisible, their contributions to cosmic history overlooked. Now we know they represent a critical phase in galaxy growth, especially in the early universe, where collisions were frequent and gas was plentiful. Many of today's massive elliptical galaxies likely passed through a ULUG stage, their current forms sculpted by those ancient bursts of obscured energy. Even more remarkable, the heavy elements forged in ULUG stellar factories, carbon, oxygen, silicon, were later incorporated into new generations of stars and planets. The iron in Earth's core, the calcium in our bones, might trace their lineage back to such hidden infernos, yet for all their violence, ULUG follow a cosmic rhythm. Their brilliance peaks and fades over mere hundreds of millions of years, a heartbeat in galactic time. As the dust clears and the black hole's glare takes center stage, what remains is a galaxy fundamentally transformed. Its gas depleted, its star formation waning, its structure reshaped by the merger's aftermath. These once hidden powerhouses remind us that the universe's most dramatic transformations often occur out of sight, their stories written not in starlight, but in the heat of dust and the whisper of infrared waves, a language we've only just begun to understand. Magnetic fields weave through galaxies like invisible threads, subtle yet persistent forces that shape the chaos of collisions in ways we're only beginning to understand. Though they're thousands of times weaker than Earth's magnetic field, their influence is anything but insignificant. Picture a galaxy's magnetic field as a vast, tangled web stretching between stars and gas clouds, a structure so delicate that the gravitational upheaval of a merger can twist and amplify it into cosmic knots. These magnetic forces don't steer galaxies like gravity does, but they leave fingerprints on everything from the birth of stars to the jets spewing from supermassive black holes. During a collision, these fields become cosmic sculptors, guiding how gas flows between the merging galaxies. As tidal forces stretch and compress interstellar material, magnetic fields channel turbulent gas into dense filaments, creating the perfect conditions for star formation. Some regions, magnetically pinned like fabric held taut, resist compression, while others collapse more easily under gravity's pull. This interplay explains why starbursts in merging galaxies often appear in intricate patterns rather than uniform blobs, magnetism's unseen hand organizing the chaos. The Antennae Galaxies reveal this beautifully, with their star-forming regions aligned along magnetic field lines like pearls on a string. But magnetism's role doesn't stop there. When galaxies collide, their tangled fields act as particle accelerators on a galactic scale. Charged particles' cosmic rays surf along these magnetic highways, gaining tremendous energy before blasting into space. These rays can heat surrounding gas, stifling star formation in some areas while triggering it in others. In extreme cases, they might even help drive the colossal winds that eject gas from galaxies entirely, a process critical to explaining why some merged galaxies become red and dead. It's a reminder that even the weakest forces can have outsized effects when amplified by cosmic violence. The most dramatic magnetic transformations occur near supermassive black holes. As merging galaxies funnel gas toward their cores, magnetic fields grow stronger, wrapping around the black holes like coiled springs. When these fields snap, a process called magnetic reconnection, they release energy in bursts that can outshine entire galaxies. Some theorists believe these eruptions might explain mysterious fast radio bursts, while others suggest they're key to launching the relativistic jets seen in active galaxies. Either way, magnetism proves it's anything but a passive bystander in galactic mergers. It's an active participant, shaping the aftermath of collisions in ways gravity alone can't. Yet studying these fields remains a monumental challenge. Unlike starlight or gas, magnetism is invisible except for its effects. Astronomers must rely on clues: the polarization of light from dust grains aligned with magnetic fields, or the way cosmic rays spiral through space. New instruments like the Square Kilometer Array radio telescope promise to unveil these hidden forces in unprecedented detail, mapping their structure across merging galaxies light years away. What they'll reveal could rewrite our understanding of how galaxies evolve, showing us that the cosmic ballet isn't just a dance of mass and gravity, but of invisible forces twisting and turning in the dark. The story of galactic collisions has always been one of hidden complexity: dark matter guiding visible structures, black holes shaping their surroundings, and now, magnetic fields quietly orchestrating the flow of matter and energy. These forces remind us that the universe's grandest transformations are never simple, even when they appear so from afar. Behind every galactic merger, there's a symphony of interactions, each note played by a different force, together composing the music of cosmic evolution. And as we learn to listen, we're discovering that even the softest voices in that symphony can change the tune. Simulating galactic collisions is like running the universe's greatest hits in reverse, taking the snapshots we see through telescopes and rewinding them to understand how they formed. Supercomputers have become the ultimate cosmic time machines, crunching numbers at speeds unimaginable just decades ago to recreate these colossal encounters. Every simulation starts with a simple question. If we take two galaxies with specific shapes, sizes, and compositions, and let gravity do its work, what happens next? The answer unfolds in exquisitely detailed animations, where billions of virtual particles stand in for stars, gas clouds, and dark matter, each obeying the unbreakable laws of physics. What makes these simulations so powerful is their ability to test theories against reality. When astronomers observe the Antennae Galaxies' tangled arms or the Mice Galaxies' stretched tails, they can plug those conditions into a simulation and watch whether their models produce matching structures. It's a cosmic detective game where every mismatch between simulation and observation forces scientists to rethink their assumptions. Perhaps dark matter behaves differently, or supernova feedback is stronger than expected. The best simulations don't just replicate what we see, they predict details telescopes haven't yet spotted, like faint stellar streams or the distribution of gas in a merger's aftermath. The complexity of these models is staggering. Modern simulations don't just account for gravity, they incorporate gas dynamics, magnetic fields, star formation, and even the explosive feedback from dying stars. When a supernova detonates in a simulated galaxy, its shockwaves heat surrounding gas, stifling further star formation in that region. These ripple effects matter immensely, as they determine whether a merged galaxy becomes a star-forming powerhouse or a quiet elliptical. Supercomputers track these interactions across millions of light-years and billions of years, compressing cosmic timescales into days or weeks of calculation. Yet even the most advanced simulations require trade-offs. Simulating every star in two colliding galaxies would demand impossible computational resources, so astronomers use clever shortcuts. Some models treat stars as particles representing thousands or millions of actual stars, while others focus on high-resolution zoom-ins of specific regions, like galactic cores where black holes duel. The art lies in balancing detail with scope, capturing enough complexity to reveal meaningful patterns without bogging down in minutiae. One of the most profound insights from simulations is how sensitive galactic collisions are to initial conditions. Tweak a galaxy's gas fraction or collision angle slightly, and the merger might produce a stunning spiral instead of a featureless elliptical. Some runs generate tidal dwarfs rich in metals, others fling stars into oblivion. This variability mirrors the diversity we see in actual galaxies, suggesting that the universe's galactic menagerie, from elegant spirals to bloated ellipticals, stems from slight differences in how their ancestors collided and merged. Perhaps the greatest testament to simulations is their predictive power. Before telescopes spotted the Milky Way's Gaia sausage stream, a remnant of an ancient collision, simulations had already suggested such structures should exist. When the James Webb Space Telescope peers into the early universe, it often finds merging galaxies that match simulated proto-galaxies from virtual universes. This synergy between digital and observational astronomy is reshaping our understanding of cosmic evolution, proving that while galaxies may collide in silence, their stories are anything but quiet. To truly grasp the drama of colliding galaxies, we must learn to see the universe in all its colors, not just the visible light our eyes detect, but across the entire electromagnetic spectrum. Each wavelength acts like a specialized lens, revealing hidden chapters in the story of galactic mergers. X-ray telescopes pierce through cosmic dust to expose the hottest regions where gas superheated to millions of degrees swirls around black holes or blasts outward in shockwaves from supernovas. These high-energy emissions act as cosmic X-rays, showing us the fractures and fevers within merging galaxies, the telltale signatures of matter screaming as it plummets toward oblivion. But switch to infrared vision and an entirely different spectacle emerges. Where visible light shows only dark bands of dust, infrared cameras unveil nurseries of newborn stars glowing behind those obscuring curtains. The James Webb Space Telescope has revolutionized this view, capturing mergers where over 90% of star formation occurs hidden within dust clouds, invisible at optical wavelengths but blazing brightly in infrared. This explains why some colliding galaxies appear surprisingly dim in visible light, yet rank among the universe's most luminous objects when observed in infrared. Their true brilliance is literally shrouded in cosmic smoke. Then there's the radio realm, where telescopes like ALMA trace the cold molecular gas, the raw material for future stars. Unlike the violent X-ray emissions or the warm infrared glow, radio waves map the quiet reservoirs of gas that haven't yet ignited into starbursts. These observations reveal how mergers redistribute fuel across galaxies, creating intricate networks of filaments and streams. Some gas falls toward the galactic center, feeding black holes. Some gets blown into intergalactic space by stellar winds, and some lingers, waiting to collapse into the next generation of stars. Radio astronomy also exposes the invisible hand of magnetic fields, as polarized radio waves twist along field lines like compass needles pointing to hidden forces shaping the collision. The real power comes when we combine these views. Take the famous galaxy NGC 6240, a chaotic merger glowing fiercely in X-rays from its dual black holes, while infrared images show concentric rings of dust where stars are forming at breakneck speed. Radio maps, meanwhile, reveal a gargantuan loop of cold gas stretching between the galaxies, a bridge of material torn apart by gravitational forces. Alone, each wavelength tells only part of the story. Together, they reveal the full epic, how black holes awaken during mergers, how starbursts ignite and fade, and how galaxies exchange material like cosmic cross-pollination. This multi-wavelength approach has overturned old assumptions. Before infrared astronomy, scientists underestimated how many stars form during collisions because they simply couldn't see the activity hidden in dust. Before X-ray telescopes, the connection between mergers and supermassive black hole growth remained speculative. Now we understand these events as interconnected phenomena, a feedback loop where colliding gas triggers star formation, whose dying explosions then feed black holes, whose outbursts in turn heat or expel gas. It's a celestial ecosystem best observed when we use every tool at our disposal, from gamma rays to radio waves. The next generation of telescopes promises even deeper insights. The upcoming Athena X-ray Observatory will track hot gas flows with unprecedented precision, while the Square Kilometer Array Radio Telescope will map magnetic fields across entire mergers. Combined with Webb's infrared eyes and optical giants like the Extremely Large Telescope, we're entering an era where galactic collisions can be studied in hyperspectral detail, every wavelength adding brushstrokes to a masterpiece we're only beginning to appreciate. What seems like destruction in one light becomes creation in another, proving that the universe's most transformative events demand every perspective we can muster. Right now, we're living in the golden age of galactic collisions, a brief cosmic moment when the universe is still crowded enough for these spectacular mergers to happen regularly. But this era won't last forever. As the universe expands at an accelerating rate, galaxies are being pulled apart by dark energy, the mysterious force stretching space itself. Over trillions of years, the distances between galaxies will grow so vast that even gravity's pull won't be enough to bring them together. The cosmic ballet we see today, with its swirling galaxies and dazzling starbursts, will gradually slow to a near standstill, leaving future skies far emptier than our own. This unfolding future makes our current epoch special. Telescopes like Hubble and Webb capture galaxies in every stage of collision because the universe is still young enough for these interactions to be common. Billions of years from now, astronomers, if any exist, might look out into a night sky where galaxies appear frozen in isolation, their motions imperceptibly slow. The great age of mergers will have passed, leaving behind only the products of those ancient encounters, elliptical galaxies glowing softly in the darkness, their spiral ancestors long since merged away. Yet, even as collisions become rarer, their legacy will endure. Every merged galaxy carries the imprint of its violent past tidal streams of stars, unusual orbital patterns, and the telltale glow of aging stellar populations. Future civilizations might study these cosmic fossils the way we studied dinosaur bones, piecing together a history of when the universe was alive with galactic encounters. The Milky Way and Andromeda's merger, for instance, will leave behind a galaxy so large it could dominate our local group for hundreds of billions of years, its structure a permanent record of this once dynamic era. There's a poetic symmetry to this story. Just as the early universe's frequent mergers built galaxies from smaller pieces, the far future's isolation will preserve them as finished masterpieces. We're fortunate to exist in the in-between when there's still enough chaos to witness creation firsthand, but enough order to make sense of it. The galaxies colliding today are writing the final chapters of their kind, their dances growing slower with each passing eon. And when the last great merger is over, the universe will settle into a quiet maturity, its galaxies drifting apart like ships in an ever-widening sea. But for now, the show isn't over. New mergers are beginning even as others end, their light still traveling across the void toward us. Every telescope pointed at the sky captures another frame in this cosmic film, each image a reminder that we're witnessing something fleeting, a universe in motion, its grandest structures still taking shape before our eyes. Galactic Archaeology transforms the night sky into a celestial detective story, where every star holds clues to the Milky Way's turbulent past. Unlike traditional archaeology, which digs through layers of Earth, astronomers sift through layers of time, tracking the motions and compositions of billions of stars to piece together our galaxy's history of collisions. The Milky Way's halo, a vast spherical cloud of ancient stars surrounding its disk, is littered with the remnants of devoured dwarf galaxies. These stellar fossils move in strange, looping orbits, their paths betraying their origins as outsiders, captured long ago in gravitational struggles. Their chemical makeup tells an even deeper story. Each generation of stars carries a unique fingerprint of heavy elements, forged in the hearts of earlier stars and scattered by supernovas. By decoding these elemental signatures, scientists can trace which stars were born together in the same dwarf galaxy, even if they're now scattered across the halo like shards of a shattered vase. Take the Gaia sausage, for example, a sprawling stream of stars orbiting the Milky Way in a peculiar, sausage-shaped path. These stars move differently from the rest of the galaxy, their velocities and trajectories revealing they're the shredded remains of a dwarf galaxy that smashed into the Milky Way 8 to 10 billion years ago. Chemical analysis confirms it. These stars have higher ratios of certain metals, like magnesium and europium, compared to native Milky Way stars. That's because their parent galaxy formed stars more slowly, allowing supernovas to enrich its gas with distinct elemental blends before the Milky Way tore it apart. This cosmic cannibalism wasn't a one-time event. At least a dozen similar streams crisscross our galaxy's halo, each the ghostly trail of a past merger. Some, like the Helmi stream, are so ancient their stars have nearly blended into the galactic background, detectable only through painstaking surveys of stellar motions. The tools of this trade are as advanced as the mysteries they unravel. Space telescopes like Gaia map the positions and velocities of over 1 billion stars with precision, while ground-based spectrographs dissect their light to reveal chemical compositions. Together, they create a galactic family tree, showing how the Milky Way grew not just from gas collapsing in the early universe, but from swallowing smaller neighbors whole. Even our galaxy's globular clusters, tight knots of stars once thought to be primordial, are now known to include captured strays from devoured galaxies. Their orbits and chemistries betray their foreign origins, like accents revealing a person's homeland. What's emerging is a story of hierarchical growth, the idea that galaxies like ours assembled piecemeal over billions of years, with each merger leaving subtle marks. Some collisions triggered bursts of star formation, while others stirred the galactic disk into warps or ripples still visible today. The Sagittarius Dwarf spheroidal galaxy, currently being torn apart by the Milky Way, is adding its stars to the mix, its debris creating faint ripples in our galaxy's outer disk. Future mergers, like the impending collision with Andromeda, will overwrite these older signatures, layering new chapters onto our galaxy's biography. Yet galactic archaeology isn't just about the past, it's about understanding the universe's fundamental rules. By studying how mergers redistribute stars and gas, astronomers test theories of dark matter's behavior. The way tidal streams curve, for instance, depends on the shape of the Milky Way's invisible dark matter halo. Some streams appear kinked or fragmented, hints that dark matter isn't perfectly smooth but clumpy, like flour with unmixed lumps. Other discoveries challenge expectations, like the recent find of stars in the Milky Way's halo with chemistry, suggesting they were ripped from the galaxy's own disk during ancient collisions, flung outward like splashes from a stone dropped in water. This field is rewriting galactic history in real time. Every new stellar stream discovered, every chemical anomaly mapped, adds another piece to the puzzle. The night sky, once a static tapestry, is now a dynamic archive, its stars' motions and compositions whispering tales of long-ago encounters, of galaxies no longer existing except as scattered stars in our own. And as telescopes grow more powerful, we'll likely uncover even fainter relics, perhaps evidence of the very first mergers that seeded the Milky Way's growth. The cosmos remembers its violence, and we're just learning to read its memories. Galaxy clusters are the titans of the cosmos, vast metropolises containing hundreds or even thousands of galaxies bound together by gravity. But these colossal structures aren't static. They too collide in mergers that dwarf even the most spectacular galactic encounters. Imagine two clusters, each millions of light years across and weighing a quadrillion times more than our Sun, hurtling toward one another at thousands of miles per second. The sheer scale is mind-bending. Where galaxy mergers reshape individual star systems, cluster mergers reconfigure the very scaffolding of the universe. When these behemoths meet, something counterintuitive happens their galaxies barely notice. Like commuters passing through a crowded train station, most galaxies glide past each other unscathed, their vast separations preventing direct collisions. But the cluster's true giants, their immense reservoirs of superheated gas, aren't so lucky. This gas, glowing at millions of degrees and visible only in X-rays, slams together violently, creating shock waves that ripple across millions of light years. These cosmic tsunamis heat the gas further, distorting it into intricate shapes that resemble cosmic bullet trails or vast, glowing boomerangs. The Chandra X-ray Observatory has captured these structures in stunning detail, revealing how cluster mergers sculpt the universe's largest objects. One of the most dramatic examples is the Bullet Cluster, a cosmic collision so energetic it's become a landmark in astrophysics. Here, two clusters have plowed through each other, leaving their galaxies largely undisturbed but separating their gas clouds like smoke torn apart by wind. The gas lags behind, slowed by friction and pressure, while the galaxies, and more crucially, the invisible dark matter, continue ahead, detected only through gravitational lensing. This separation provides some of the strongest evidence for dark matter's existence, proving it interacts differently from ordinary matter. The Bullet Cluster isn't just a merger, it's a forensic snapshot of the universe's hidden architecture. These collisions release almost unimaginable energy, sometimes enough to power 1 billion supernovas. The shock waves accelerate particles to near light speeds, generating radio emissions that span millions of light years. In clusters like Abell 3667, astronomers have detected gargantuan radio relics, filaments of synchrotron radiation, marking the boundaries of these particle accelerators. The energy involved is so vast it could reheat entire regions of the intergalactic medium, influencing galaxy formation across cosmic epochs. Yet cluster mergers also create order from chaos. Over billions of years, the merged gas settles into a new, more massive halo, while the combined gravity of the cluster reshapes its surroundings. These events are the universe's way of building its largest structures, growing clusters into superclusters that stretch across hundreds of millions of light years. The Great Attractor, a mysterious gravitational anomaly pulling thousands of galaxies toward it, may owe its existence to past cluster mergers on a staggering scale. What's humbling is realizing these collisions are still unfolding. The Coma Cluster, one of the densest known, shows signs of multiple mergers in its lopsided structure and turbulent gas. Even our own local group of galaxies, including the Milky Way, will one day merge with the Virgo Cluster, drawn together by gravity's unrelenting pull. These events aren't just cosmic spectacles, they're the engines of large-scale structure formation, weaving the cosmic web that defines the universe itself. And there's a profound symmetry here. Just as galaxy mergers forge new stars and black holes, cluster mergers forge the environments where galaxies themselves evolve. The shockwaves, magnetic fields, and turbulent gas left in their wake influence how galaxies form stars, how black holes grow, and even how dark matter distributes itself. To study cluster mergers is to witness the universe organizing itself on the grandest possible scale, a slow, violent ballet where gravity writes the music and entire galaxies are merely dancers in its rhythm. Gravitational waves are the universe's most elusive messengers, ripples in the fabric of space-time itself, generated by cataclysmic events like merging black holes. When two supermassive black holes spiral toward collision at the heart of merging galaxies, their immense masses warp the surrounding cosmos, sending out waves that travel at light speed across billions of light years. Unlike light, which can be blocked or scattered, these waves pass unimpeded through dust, gas, and even entire galaxies, carrying pristine information about their origins. The final moments before a black hole merger are among the most violent events in the universe, yet completely invisible to traditional telescopes. Gravitational waves are our only direct line to these hidden cosmic spectacles. The detection of these waves marks a seismic shift in astronomy. Ground-based observatories like LIGO and Virgo have already captured gravitational waves from smaller stellar mass black holes, but the mergers of supermassive black holes, millions or billions of times heavier than our Sun, require a new approach. Enter LISA, the Laser Interferometer Space Antenna, a future space-based observatory designed to sense low-frequency waves that ground detectors can't pick up. LISA will consist of 3 spacecraft flying in a triangular formation millions of miles apart, firing lasers to measure infinitesimal distortions in spacetime as waves pass through. These distortions are absurdly tiny, less than the width of an atom over the detector's entire span, yet LISA precision will map them with astonishing clarity. What makes these waves so revolutionary is the story they tell. Every ripple encodes details about the black hole's masses, spins, and even the environment where they merged. By analyzing the waveforms shape how it spirals to a crescendo before abruptly cutting off, scientists can reconstruct the black hole's final orbits and the moment they became one. This data offers clues about how supermassive black holes grow, whether they're born from ancient cosmic seeds or built through successive mergers. Some theories suggest early universe black holes might have spun faster or paired differently than their modern counterparts, leaving distinct signatures in their gravitational waves. But the implications go beyond black holes. Gravitational waves from galactic mergers could reveal secrets about dark matter, the invisible substance shaping galaxies. If dark matter interacts with black holes in unexpected ways, it might subtly alter their merger signals, a deviation LISA could spot. These waves might also help solve the final parsec problem, a long-standing mystery about why supermassive black holes seem to stall when just a few light-years apart. Some researchers think gravitational wave observations will show that chaotic gas dynamics or triple black hole systems provide the extra nudge needed to push them together. The most mind-bending possibility: gravitational waves could carry echoes from the universe's first black holes, primordial monsters born in the chaos of the Big Bang. If these ancient black holes exist, their mergers would send waves ringing through spacetime like cosmic background radiation, a faint hum beneath later collisions. Detecting this signal would open a window into the universe's infancy, a time before stars or galaxies even formed. What's incredible is how this new astronomy complements traditional methods. While telescopes capture the light from galactic mergers, the starbursts, the tidal tail's gravitational waves expose the invisible choreography of black holes at their cores. Together, they paint a complete picture of how galaxies evolve. In the coming decades, as LISA and other detectors come online, we'll witness the cosmos in a way Einstein himself thought impossible, not just through light, but through the very stretching and squeezing of spacetime. Every merger detected will be a Rosetta Stone, translating the hidden language of gravity into a story we can finally understand. Galactic collisions are more than cosmic events. They are masterpieces painted across the canvas of space, inspiring human creativity for generations. The ethereal arcs of tidal tails and the radiant glow of starburst regions have transfixed artists long before telescopes could explain their origins. Vincent van Gogh's Starry Night, with its swirling celestial vortices, eerily mirrors the structure of colliding galaxies like NGC 4038, proof that the human imagination can channel cosmic chaos into art centuries before science catches up. Modern astrophotographers elevate these encounters into visual symphonies, using filters to highlight ionized hydrogen in crimson and young star clusters in sapphire, transforming raw data into works that hang in galleries as readily as they grace scientific journals. Science fiction, too, has borrowed liberally from these celestial dances. The iconic galaxy swirl backdrop of countless space operas traces its lineage directly to Hubble's images of the Antennae galaxies. Films and video games often depict alien worlds orbiting binary stars in merging systems, their skies ablaze with overlapping spiral arms, a nod to the arresting beauty of real cosmic collisions. Even music responds to their rhythm. Composer Terry Riley's Sun Rings, created in collaboration with NASA, translates galactic merger data into orchestral movements, where crescendos mirror the gravitational interplay of stars. Yet the allure runs deeper than aesthetics. There's a profound resonance between the creative process and the physics of galactic mergers. Both are acts of destruction birthing new forms. A sculptor chips away marble to reveal a statue. Galaxies tear each other apart to forge elliptical masterpieces. This parallel has birthed interdisciplinary projects like Galaxy Merger Explorer, where scientists partner with digital artists to simulate collisions not just for research, but to explore their narrative potential. Some cultures have intuited this duality for millennia. Navajo cosmology, for instance, describes celestial beings whose conflicts shape the heavens, echoing modern astronomy's understanding of how mergers structure the universe. The universality of this fascination hints at something primal. Perhaps gazing at merging galaxies taps into our collective awe at transformation itself, the same wonder that draws crowds to watch storms or volcanoes. Or maybe their scale offers a rare vantage where destruction feels beautiful rather than terrifying, reminding us that endings and beginnings are woven into the fabric of existence. Whatever the reason, these collisions have transcended their astrophysical significance to become cultural touchstones, proving that the universe speaks not just in equations, but in a visual poetry that resonates across disciplines and dreams. One of the biggest surprises about galactic collisions, they're nothing like the fiery cosmic pileups Hollywood loves to depict. The truth is far more subtle and fascinating. While it's easy to imagine stars smashing together like cars in a freeway wreck, the reality hinges on the sheer emptiness of space. Even in a densely packed galactic core, stars are typically millions of times farther apart than our solar system's planets. If you replaced every star in the Milky Way with a basketball, they'd still average over 3,000 miles apart. That's why when galaxies merge, their stars slip past each other like two flocks of birds intersecting in midair. Countless individuals, each following their own path, almost never touching. Another persistent myth is the idea that these mergers happen in a flash. Time operates differently on cosmic scales. What looks like a collision in a Hubble image is actually a slow-motion ballet unfolding over hundreds of millions, sometimes billions of years. The initial approach alone can take longer than all of human civilization. Take the Milky Way and Andromeda. Though they're already gravitationally bound, their first close pass won't happen for 4 billion years, followed by a drawn-out dance of repeated encounters before finally merging. This timescale isn't an exception, it's the rule. The famous Antenna Galaxies, with their dramatic tidal tails, have been interacting for at least 300 million years and won't fully combine for another billion. Scale also warps expectations about outcomes. Many assume mergers erase a galaxy's identity, but the process is more like a cosmic recycling program. Spiral galaxies might lose their elegant arms, but their stars aren't destroyed, they're redistributed into new orbits, forming the smooth halos of elliptical galaxies. Even the term collision is misleading, since galaxies don't so much crash as they intermingle, their structures bending and blending like taffy pulled by gravity's invisible hands. Perhaps the most consequential misunderstanding is that these events are rare or irrelevant to us. In truth, mergers shaped nearly every galaxy we see, including our own. The Milky Way's halo brims with stellar streams, ghostly remnants of past acquisitions. Without these ancient collisions, galaxies might never have grown to their current sizes. Far from being cosmic anomalies, mergers are the universe's way of building complexity, turning small, gas-rich proto-galaxies into the diverse galactic ecosystems we observe today. Clearing up these myths isn't just about accuracy, it's about revealing the true poetry of galactic evolution. These encounters aren't violent smash-ups but gravitational conversations, where galaxies exchange matter and energy across eons, leaving both transformed. By understanding the real timescales and physics involved, we begin to see the universe not as a static museum, but as a living, dynamic entity, where even the grandest structures are continually rewritten by gravity's patient hand. Imagine having the power to orchestrate your own cosmic ballet, to fling galaxies across a digital universe and watch as they spiral together in a dance of gravity and starlight. Interactive simulations like NAS, A Galaxy Crash, and the Universe Sandbox game transform abstract astrophysics into hands-on exploration, letting anyone experiment with galactic collisions in real time. These tools aren't just toys, they're gateways to understanding, built on the same equations astronomers use to model real mergers. Slide a control to adjust a galaxy's mass, and you'll see how a slight change alters the entire encounter, stretching tidal tails longer or triggering fiercer starbursts. Tweak the collision angle and witness how a head-on smash creates a different aftermath than a glancing blow, less like a demolition derby and more like a gravitational conversation. What makes these simulations so valuable is how they reveal the delicate balance of forces at play. Crank up the dark matter slider, and suddenly the galaxies bend more dramatically, their invisible halos steering the visible stars like puppeteers. Reduce the gas content, and the merger's fireworks dim, showing why some collisions light up with newborn stars while others fade quietly into elliptical stillness. These what-if scenarios do more than entertain. They illuminate why real galaxies like the Antennae or mice look the way they do, bridging the gap between textbook diagrams and the cosmos's messy reality. For educators, these tools are revolutionary. A student struggling to visualize how mergers reshape galaxies can run a simulation in minutes, watching as their own choices altering speed, spin, or composition create cosmic sculptures matching Hubble's photographs. Amateur astronomers, too, benefit, using the software to predict how future mergers like Milky Way-Andromeda might unfold or to identify tidal features in telescope images. Even researchers occasionally turn to simplified simulations for brainstorming, testing rough ideas before committing to supercomputer runs, but perhaps the most profound impact is emotional. There's a visceral thrill in playing Cosmic Architect, a sense of connection to the universe's grandeur that graphs and equations alone can't provide. When you nudge two galaxies together and see them warp exactly as Webb's latest deep field image showed, the scale of space stops feeling abstract. You're not just learning about collisions, you're feeling them, internalizing the rhythms of a process that once seemed too vast to comprehend. And in that moment of play, the universe becomes a little less distant, a little more wondrously knowable. Galactic collisions aren't just cosmic spectacles, they're the ultimate classroom for unraveling the universe's deepest mysteries. Picture a high school physics lesson where students gasp as a simulation shows two galaxy models swirling toward each other, their paperclip stars stretching into tidal tails under the pull of magnets hidden beneath the paper. This hands-on demo does more than dazzle. It crystallizes abstract concepts like gravity and momentum into something tangible. The sheer visual drama of merging galaxies bridges the gap between textbook equations and the living cosmos, transforming passive learners into active explorers. What makes these events such powerful teaching tools is their ability to tie together seemingly disconnected astronomical phenomena. A single collision showcases gravity's role in shaping the universe, the life cycle of stars born from colliding gas clouds, and even the invisible influence of dark matter. Planetariums leverage this by projecting immersive mergers onto domed ceilings, letting audiences witness how slight changes in collision angles alter galactic outcomes, a masterclass in celestial mechanics disguised as a light show. The iconic Hubble images of the Antennae Galaxies, for instance, aren't just pretty pictures. They're kinetic diagrams illustrating how kinetic energy converts into star-forming shockwaves. Interactive simulations take the learning even deeper. Platforms like World-Wide Telescope allow students to manipulate variables, adjusting galaxy masses, gas fractions, or dark matter halos, and instantly see how these tweaks reshape the merger's aftermath. Suddenly, terms like tidal forces and starburst phase shift from vocabulary words to visceral experiences. One university course even tasks students with predicting a galaxy's fate based on its collision parameters, mirroring real astrophysics research. The lesson, astronomy, isn't just about memorizing facts, it's about reading the stories written in starlight. For younger learners, collisions become gateway to scale and time. Building a model with sprinkles representing stars quickly reveals why stellar smash-ups are rare. The stars stay improbably far apart even when galaxies overlap. A timeline comparing merger durations to Earth's geological epochs drives home the universe's vast timescales. Even art classes get involved, with students painting their interpretations of galactic encounters, blending science and creativity to solidify understanding. The real magic happens when these lessons spark deeper questions. Why do some mergers produce ellipticals while others retain spiral structures? How can invisible dark matter steer visible stars? Each query branches into new realms: stellar evolution, relativity, particle physics, proving that a single galactic collision is really a key to the cosmic curriculum. Educators increasingly frame entire astronomy units around these events, using their narrative arc approach, interaction, aftermath as a scaffold for broader concepts. And the impact lasts long after class ends. Many professional astronomers trace their passion to childhood encounters with collision simulations or planetarium shows. There's something uniquely compelling about watching galaxies, those supposedly static, island universes, twist and merge like living things. By tapping into that wonder, teachers don't just explain astronomy, they ignite the next generation's curiosity about the universe's grand, ever-changing tapestry. Galactic collisions are the universe's way of rewriting its own story, not with erasures, but with bold, sweeping strokes of reinvention. What looks like chaos is really transformation on the grandest scale, where gravity acts as both the architect and the artist. Every merger reshapes the cosmic landscape, turning spirals into ellipticals, igniting starbursts that outshine entire galaxies, and weaving dark matter into new invisible frameworks. These events aren't endings, they're the universe's method of growth, recycling matter and energy into fresh configurations that will endure for billions of years. Take our own Milky Way's fate as a testament to this cycle. In 4 billion years, when we collide with Andromeda, the night sky will become a masterpiece of slow-motion change. Familiar constellations will dissolve as new stars from Andromeda join our celestial tapestry, their light blending with ours in a dazzling display. Yet amid this upheaval, Earth's orbit around the Sun will likely remain undisturbed, a reminder that even the most colossal cosmic events leave pockets of stability in their wake. The merged galaxy, nicknamed Milky Way-Andromeda, will stand as a monument to this encounter, its golden haze of aging stars telling the tale of two galaxies that became one. This dance of destruction and creation isn't unique to our corner of the cosmos. From the Antenna Galaxies' starburst fireworks to the quiet cannibalism of dwarf galaxies, we see the same patterns repeating across the universe. Each collision leaves forensic evidence: tidal streams, unusual star clusters, even rogue black holes that astronomers decode like cosmic archaeologists. These clues reveal a universe that's dynamic and interconnected, where galaxies grow not in isolation, but through encounters that stretch across eons. What's truly humbling is realizing how much we owe to these collisions. The heavy elements in our bodies, the planets in our solar system, even the Milky Way's spiral arms, all were shaped directly or indirectly by ancient mergers. The universe builds complexity through encounters, turning simplicity into diversity one collision at a time. And as telescopes peer deeper into space, we're witnessing this process unfold in real time, capturing snapshots of every stage from first approach to final merger. So the next time you look up at the night sky, remember, those seemingly static stars are part of a grand, ever-changing ballet. Galaxies collide, stars are born, and the universe reinvents itself, not in chaos, but in a rhythm as old as time itself. If you've enjoyed unraveling these cosmic mysteries with me, don't forget to like, subscribe, and share your thoughts in the comments. The universe still holds countless secrets, and together we'll keep exploring them one